All right, so thank you very much, Thomas, for the introduction. I'll present in English, but I'll be happy to take questions in French afterwards if people prefer. So yeah, many thanks for the introduction, for the invitation. It's great to be here, and I look forward to sharing some of our recent work on developing what I titled physics-based digital twins for reconfigurable wave systems. And I picked the word digital twin, which I know many people interpret in different ways, but I think it sort of makes nicely the connection to the topic of this workshop. So basically, I want to cover a little bit of our motivation. Why are we interested in certain types of complex reconfigurable wave systems? And then I will show you how we model them. So the starting point for all of this is that the next generation of wave systems, and by the way, I work mostly in the microwave domain, so most of the things I say will be specific to the microwave domain, although of course, potentially there are some generalizations that are possible. So at least within the microwave domain, the next generation of wave systems such as antennas, filters, routers, physical neural networks, radio environments, they're all expected to offer an extreme transfer function tunability. And so that leads to some fundamental questions about what are the design principles for designing, for conceiving such systems on a very high conceptual level, because so far what is typically done is that interactions between tunable components are neglected or mitigated or coarsely approximated. And on the one hand, it might be impossible to do that once we have hundreds of tunable elements. And on the other hand, maybe it's actually not desirable because maybe there's actually something good in these interactions. And so, of course, connected to the hardware layer is then the question of how do we optimize an extremely tunable wave system once we've configured it. So these are really two coupled problems. And one of our key findings in the recent past is that strong coupling between the tunable elements, which traditionally is avoided, is actually very helpful to maximize the sensitivity of the transfer function of a wave system to the configuration of the tunable elements. And that is, of course, what we want to achieve extreme tunability with as few tunable elements as possible. And so that's really the motivation for exploring how we can model such extremely tunable wave systems. Because, of course, as soon as they start to, all the tunable elements interact with each other, there's a lot of complexity. And at first sight, it might seem that that is overwhelming. And maybe the only solution is training a deep neural network, and that has its disadvantages in terms of number of parameters and required training examples and so on. What I will show you in this talk is that actually we can have compact physics-based models to describe pretty much any reconfigurable microwave system, and that we have tools to calibrate the parameters that we need for such a model to accurately describe a given experimental system, even though we might not know the exact geometry and the material composition. And finally, I'll also say a few words about how we can then, once we have formulated and calibrated a model for those, how we can use that to efficiently optimize a reconfigurable wave system. And along the way, I'll mention a byproduct that we came across recently in our effort to estimate the parameters of these models, which we now refer to as the virtual vector network analyzer. Basically, it's a technique for measuring very large scattering matrices with a few port vector network analyzer without any manual reconnection. So that's something that's an instrumentation aspect that is relevant to the microwave regime. And also I'll mention how that can be extended to multi-port wireless sensing. So to start, let me give you an overview of the sort of extremely tunable wave systems in the microwave regime that we're interested in. Probably the most prominent example are smart radio environments, where the idea is that the wireless channel between a base station and the user equipment would no longer be uncontrolled, but we would be able to parameterize it by putting a reconfigurable surface on the wall. So basically some sort of programmable meta surface made up of meta items whose scattering properties we can individually control. And then by choosing that configuration, we could tailor the wireless channel from the base station to the user equipment to have some favorable properties, such as focusing on the user equipment. That's probably the most prominent example. Another important example is dynamic metasurface antennas, which are essentially a hybrid MIMO architecture. The point being that as we move towards next generation wireless systems, there's the idea that we need in principle, very large apertures in order to focus the waves towards desired users. But if you do that with traditional antenna architecture, then you need a large number of radio frequency chains, which is pretty much it's too expensive in reality to do. And so these dynamic metasurface antennas are a very compact implementation of what is known as hybrid MIMO, where you have a single or a few radio frequency chains, and still you can generate and receive coherent wavefronts. And then I'll also mention that there are some other applications we're interested in related to programmable signal processing, which could be some sort of filtering or routing or signal differentiation, or also some forms of physical neural networks implemented in the wave domain. Now, these look all pretty different in terms of the experimental details, but what they have in common is that we're looking at a linear wave system. So basically, what it means is that we send in a wavefront X, and it maps linearly to the output wavefront Y by the transfer function of the system H. And in all of these cases, the transfer function is parameterized by some vector that represents the configuration of our tunable degrees of freedom. And so then there are two basic questions that we want to think about. The first one is the forward problem. So what is H for a given C? And then there's also the inverse design problem, which is what C closely approximates a desired H. And now there's a couple of questions that we think about in our effort to moving towards extremely tunable wave systems. First of all, of course, we want to maximize the sensitivity of H to C in order to have as much tunability as possible. So what overarching principles enable that? And then in terms of the inverse design problem, well, fundamentally, do we want to do that in a model-based manner or in a model-agnostic manner? And if it's model-based, then how do we actually formulate and calibrate that model? Because you realize all of these systems are actually pretty complex, the geometry, the material composition, and so on. And maybe the overarching question is, what is really the trade-off between maximizing the sensitivity to the configuration and dealing with complexities that strong mutual coupling brings about in terms of modeling and optimization? Now, we believe that a model-based in-software optimization of such systems seems ideal, provided that we can satisfy the following criteria: knowing how to formulate a model, knowing how to estimate the parameters that go into that model to describe a specific experimental setup, and then knowing how to use such models efficiently for optimization. And sort of the key point of my presentation is to show you that we believe that we can satisfy all three of these requirements. So here's the outline of my talk. I'll start by motivating in a little more detail our interest in these highly complex reconfigurable wave systems by discussing general hardware characteristics that maximize the sensitivity of the transfer function to the reconfigurable configuration. And then I'll get into the modeling part that is, of course, at the core of what this workshop is about. So I'll show you how we can formulate these sort of purely physics-based models in a very compact manner, how we can estimate their parameters. And part of that, I'll digress a little bit and introduce the virtual VNA. And then in the end, I'll say a few words about, once we formulate and calibrated the model, how we can use it for optimization. So starting with the first part, I want to think a little bit about the impact of mutual coupling between tunable elements on the transfer function tunability. And to make that discussion concrete, I'll consider as the hardware this dynamic metasurface antenna that I mentioned previously. So basically, this is a two-dimensional cavity. We have two parallel plate metallic waveguides, and then the third dimension is limited by a set of vias. And this is electrically large cavity that is fed from the back. So signal enters from the back, bounces around in the cavity, and then there are these programmable meta-atoms patterned onto the front surface of the cavity, and depending on which ones are switched on and off, the waves will leak out in different ways from the cavity and interfere to generate different coherent wavefronts. And this is a nice system to study to understand what we're interested in, namely how the transfer function tunability depends on mutual coupling strengths, because we can actually model that in a sort of very tractable way based on a coupled dipole approach, which allows us to tune the mutual coupling strength, and also we can impose zero scattering if we wish so. Now, I want to look at two aspects here. First of all, how does the mutual coupling strength impact our ability to tune the radiated field And I'll quantify that in terms of the sensitivity of the radiated field to the configuration, some sort of a partial derivative. And then also, I want to think about how the mutual coupling strength impacts our ability to accurately predict the radiated field in a simple manner. So basically, what I'll look at is how accurate would a simple linear regression be able to predict the radiated field as a function of the configuration. So to start, let's consider the case without any mutual coupling. And what I'm showing here is a sensitivity map. So it's not a radiation pattern, but it's the sensitivity of the radiation pattern to a change in the configuration of one of these programmable meta-atoms. Now, it does look like the radiation pattern of a point source, and that's what you'd expect because there's no coupling between the meta-atoms that we're assuming no mutual coupling. Now, as we allow for mutual coupling and make it stronger, this sensitivity map starts to look more and more like a speckle pattern arising, like what you would expect from an interference of multiple point sources, because changing the configuration of one meta-atom will induce changes in the dipole moments of other meta-atoms due to the mutual coupling. Now, the general intuition here is that the longer the wave bounces around within the antenna, on the one hand, the more sensitivity it will develop to how we've configured these meta-atoms. But on the other hand, also, the more the impact of one meta-atom on the transfer function will depend on how the other meta-atoms are configured. And so this results in a fundamental trade-off that we see in our numerical results, which is that as we increase the mutual coupling strength, on the one hand, we get this increase in the sensitivity to the configuration, which is what we're after. But on the other hand, it becomes more complicated to solve the forward problem, which is to predict the radiation pattern for a given configuration. So it becomes less and less accurate to use a simple linear regression for that prediction. And we've wanted to verify that also experimentally. So we've actually built one of these dynamic metasurface antennas. Now in experiments, it's harder to just change the mutual coupling strength. And so what we did instead is alter the mutual coupling strength in post-processing, where what we can do is go to the time domain and then truncate the impulse response at a certain delay time. And then that delay time would basically be the proxy for the mutual coupling strength. And so then in our experiments, we observe basically exactly what we found in our simulations and what we expect. So as the delay time at which we truncate increases, which is, I remind you, is our proxy for the mutual coupling strength, the more sensitivity we get, and that translates into a better ability to shape the radiated field. So here we looked at an example of channel gain enhancement. You can see that as we have more mutual coupling, we're able to better enhance the channel gain in its desired direction. At the same time, we can also look at the strength of the Hessian, which is the second order derivative, tells us something about the coupling between the entities, and that also increases, which translates into the decrease in our ability to predict the radiated field with a simple linear regression. So what we've seen so far is that strong mutual coupling between the tunable elements on the one hand boosts the tunability of the transfer function, but on the other hand makes the mapping from configuration to transfer function more complicated. And so that means that if we want to react the benefits of these increased tunability, really we need to be able to model this mutual coupling. And so this is basically what I want to show you in the remainder of this talk, is how we formulate a model for this coupling, how we calibrate that model to describe a specific experimental system, and then how we can use that for optimization. So starting with how we formulate the model, I'll slightly switch gears and talk about a conceptually very similar, but practically looking a little different experiment. So this is an electrically large cavity whose boundary conditions are basically partially parameterized by a programmable metasurface. In some sense, you can think of this as these smart radio environments. So we have 4 antennas in there that allow us to couple waves into and out of the system. So we measure a 4x4 scattering matrix. And then the question is, well, how does that scattering matrix depend on the configuration of the metasurface? And here I'm just, so you have sort of a flavor of what this metasurface looks like. It's a very simple printed circuit board. Essentially, it's a patch, and then there are pin diodes, and depending on how we bias the pin diode, the interaction of the wave with the patch is obviously different. So we want to understand for this specific experimental setup, how can we map the configuration to the scattering parameters that we actually measure at these 4 antennas? And that seems, at first sight, overwhelmingly complicated, right? Because the geometry is irregular and essentially not known. The material composition is not exactly known. So how do we do that? Well, actually, it turns out there's a general recipe that works pretty much for any reconfigurable microwave system, and that proceeds in the full. That it consists basically in partitioning the system into 3 entities. And so, and this is something that you can do with almost any reconfigurable microwave system. The first entity is the set of antenna ports, which is the interfaces between the system and the outside world by which you inject and receive waves. The second entity are the tunable lumped elements, in our case, pin diodes. And then the third entity is all the rest, which is by definition static. So no matter how complicated the rest is, it's static scattering, and that includes the structure of the antenna and the meta atom and so on. Now, this second entity, the tunable lumped elements, by the way, I want to clarify for those who maybe not so familiar with microwave terminology, lumped means point-like. So the pin diodes are tiny compared to the wavelength at which we're operating. And now these tunable lumped elements we can think of as virtual ports to our system that are terminated by a tunable load. The load is in this case just a one-port system on its own. And so with that interpretation, we're basically right in the realm of multi-port network theory, because what we're looking at now is the connection of two multi-port systems. One describes all the static parts in our system, and it has many, many ports, including the antenna ports and all the virtual ports. And then that is connected to a load network, which comprises all the tunable loads. And so that load network, by construction, has a diagonal scattering matrix, and the kth entry of that scattering matrix would be the reflection coefficient of the kth load. And so standard multi-port network theory tells us then that the scattering matrix that we measure is related to the scattering matrix, this big scattering matrix that describes all the static parts, and the scattering matrix that describes the configuration of our loads, as you can see here on this equation. And you see immediately by inspection of this equation that the mapping from the configuration C to the measurable scattering matrix S is nonlinear. So that's why generally you would not expect a linear regression to be able to predict well the transfer function as a function of configuration. And we can get a few more insights into this by rewriting the matrix inversion in that equation as an infinite sum of matrix powers, which, by the way, is always guaranteed to converge because all the systems that we talk about are passive and generally lossy. And now this infinite series has an interesting interpretation because basically it reveals the multiple scattering in the system, and the kth term in the series essentially corresponds to all the paths in the system that encountered our programmable metasurface k times. And by the way, in the wireless communications literature, more on the theoretical side, you would find many, many papers on these smart radio environments that basically use a model of the mapping from configuration to scattering matrix that truncates that infinite series up to the first term that depends on C. And then you get this affine mapping, which is much easier to deal with. But of course, there's a truncation error whose importance depends on the mutual coupling strength. So what we've seen so far, just to remind you of where we're heading with this, is first of all, we saw that strong mutual coupling is desirable because it increases the tunability of the transfer function, which is what we're after. But on the other hand, it makes our life more difficult in terms of predicting the transfer function for a given configuration. And what I've just shown you is that actually we can write down a very compact model that is sort of grounded in physics and takes all these mutual coupling effects into account. And what I mean by compact here is that the number of parameters in this model, it depends only on the number of antennas and the number of tunable elements. It does not depend on how complicated all the static scattering objects in our environment are. Now, we're still missing some ingredients, which is that, okay, we've formulated this model, but if we want to use it to apply it to a given experimental system, we still need to figure out the parameters that go into this model so that it actually describes a given experimental system. So that's what we'll work on next. So here's just the model as a reminder. And so as you can see, basically there two sets of parameters that you need to go into this model. One is the scattering matrix, this big scattering matrix that describes all the static parts in our system. And the other is basically the vector of reflection coefficients for the loads. Now, in practice, it turns out that, of course, first of all, we would not generally know this big scattering matrix because we don't know the exact geometry and material composition. And even if we did, it might be too expensive to simulate that numerically. And also, we might not actually know the reflection coefficients of the loads that we can implement. It might be that we've bought the risk and it's not our design. It might be proprietary. It might be that it's not sufficiently well documented and so on. So actually what we can do in general is we choose a certain control vector, V, and we measure the corresponding measurable scattering matrix S. And basically everything, so this is what you can see in the picture. You choose V, you measure S, and everything else in the box you don't have directly access to. Now, the question is whether we can now estimate the required parameters so that we can use our model to predict S for any given V in our experimental system. And the easiest way to do that, and that's the first way that we explored, is just a simple gradient descent, global gradient descent. So all the unknowns are declared as variables to be found, and then we have matching pairs of V and S, just random control vectors V and the measured corresponding scattering matrices. And then via global gradient descent, we can find a set of parameters that hopefully explains our experimental measurements. And that works surprisingly well. So here you can see an example of the comparison between predicted and ground truth scattering parameters for unseen metasurface configurations. And it works actually orders of magnitude better in terms of accuracy as a benchmark, such as a linear model or a deep learning approach. Linear model, of course, it's clear that that should have problems capturing the recurrent scattering because it's fundamentally a nonlinear process. The deep learning approach uses much more parameters, but it's also having a hard time capturing all the recurrent scattering in all its details, basically because it does not benefit from this physical inductive bias that our physical model has. And this gradient descent also works actually if we're limited to non-coherent detection, so if we only measure intensity, because our model sort of inherently intertwines phase and amplitude response. So if we correctly predict amplitudes, we must have also understood the phase relation. So here you can see, indeed, these are again predicted scattering coefficients and for unseen configurations. And you see that we correctly predict their dependence on the metasurface configuration as well as the relative phases between them without ever measuring phase. And so that sets us up for thinking about in software optimized coherent control. And by coherent control here, I mean two things. I mean choosing the input wavefront X and choosing the metasurface configuration C. And so based on the model that we calibrate, we can now do both jointly in order to achieve some functionality. So here you can see some examples, pretty standard examples like coherent focusing, coherent absorption. And the key point in this figure is that based on our model, which we actually calibrated without any phase detection, we're performing as well as if we knew the ground truth. Now, so far, we've only cared about correctly predicting the scattering matrix for a given control vector V. So we did not care about ambiguities in the parameters that we estimate as long as we correctly predict the scattering matrix S. But now I want to dwell a little bit on these ambiguities. First of all, to understand the fundamental structure of these ambiguities. But then also, so far we just did this global gradient descent. But as we move to having more and more tunable elements, probably we want to do some sort of segmented parameter estimation. And in that case, we need to be aware of the ambiguities. And so we need to understand their structure. And thirdly, of course, we'd also like to think, at least as an intellectual exercise, and you'll see it actually has useful output, are there conditions by which we can constrain our parameter estimation problem so that we can lift all ambiguities? So let me first of all give you a flavor of what these ambiguities look like. Here's a related experimental setup. It's conceptually the same thing. We have this program metasurface here implemented as an array of antennas where each antenna port is connected to a phase shifter. So that's basically taking this interpretation of the virtual port terminated by load literally. And so that allowed us to have 64 states, 64 different reflection coefficients for each of these loads. And then here we proceed with a hybrid parameter estimation. I won't go through the details, but essentially we try to do some steps in closed form, and then the remaining step we do it by gradient descent. And here you can see then 5 different runs with different random seeds. You can see the 5 outcomes in terms of the reflection coefficients that we estimate. And you see there's certain structure in that. So for example, all of them go through 0, which is actually imposed by our closed form steps. You also see that this circular structure is present in all of them. But there's also this clear ambiguity. But I want to emphasize that if the goal is only to predict the scattering matrix for a given configuration, we don't care about that ambiguity. So you can see here that if we have sufficient measurements, the accuracy with which we predict the scattering matrix is very high. It's almost 50 dB. But if we then move, like I mentioned, to bigger systems, we want to think about estimating these parameters in a segmented way. And so, yeah, I don't want to dwell too much on the details, but basically, we need to be aware of these ambiguities so that different segments that we estimate have the same ambiguity, or else we cannot stitch it together in the end. So we need some overlap and so on. And if done properly, that also yields high accuracy. Now, I want to move on to the part about whether we can get rid of all ambiguities under certain conditions. And so I will just jump to the conclusion here and not go through all the math in detail. The answer is yes. And there's even a closed form way, just pure linear algebra of doing this. And so the requirements to lift all ambiguities are the following. We need to be able to terminate each of these virtual ports with at least in at least 3 different ways, and these terminations must be known. And also we need coupled loads, coupled terminations. So both of these requirements, by the way, are not satisfied by a standard programmable metasurface like I used in my experiments, where we have just 2 states. We don't even know the states. It's not a third state. There's no coupled state. But I want to think about this problem because it's actually technologically relevant to instrumentation and measurement in the microwave regime. Because basically, you realize if we're able to estimate this big scattering matrix without any ambiguity, then we've done what a many port vector network analyzer would do, except that we're using a few port vector network analyzer. And so let me make it more concrete. So here you can see the setup. We have this device under test. It's characterized by a very large scattering matrix, but we only have a vector network analyzer that measures scattering matrices in the microwave regime that has few ports. And so traditionally, if you wanted to measure that huge scattering matrix, you'd have to have many manual reconnections, which is very cumbersome and error prone and slow. Now, what we can do here instead is terminate. We only inject and receive waves through this small subset of ports that we connect to the VNA, and we terminate all the other ports by a tunable load network that satisfies exactly the criteria that I outlined. So 3 individual loads and coupled loads, and all of that is characterized. And so then we have different sets of techniques through which configurations we go to do our measurements and how we process these. But essentially, if done correctly, we can find this full scattering matrix without any ambiguity, even if we're dealing with a non-reciprocal system. So let me just briefly show you some examples. This is the first experiment where we had basically an 8-port system, which was just 8 antennas in a complicated reverberation chamber, just so that it's essentially impossible to know the scattering properties a priori. 4 of them were connected to the VNA, 4 to the tunable load network. And the coupled load, by the way, was just implemented as a coaxial cable because that's a 2-port network. That's a simple coupled load. And as you can see, upon visual inspection, actually, the estimated parameters match very closely the ground truth. We did the same thing for a non-reciprocal system. So here is this transmission line network involving some circulators. And again, it works very accurately. And also, we thought about how do we make this approach really scalable so that we can truly estimate very big scattering matrices. And so to that end, we've implemented this required tunable load network in a very cheap and compact manner on a printed circuit board. And then again, we did the tests and it still worked. Now, how much time do I have left? We have a couple of minutes, yeah? 5 or so.
13 minutes. Des questions.
15 avec question.
13 avec une question.
Okay. So now I want to show you an idea of how we can go one step further with this. So imagine you have a device under test, but this time you're not allowed to connect any of its ports directly to your vector network analyzer. The reason being, for example, that it's sort of remote and it's not possible. In that case, what you can do is connect antennas to the ports of this device under test. And then basically, you're measuring the properties of this device under test in an indirect manner. It's in many ways, it's like a fixture via which you characterize the device under test, except that that's an over-the-air fixture, which includes all the antennas and all the scattering happening over the air. And this problem is now basically solvable in 2 steps based on the virtual VNA approach, because in the first step, we characterize this over-the-air fixture with a virtual VNA protocol that I just described. So basically, we terminate the antennas that we later connect to our device under test by a tunable load network that we know. And then the virtual VNA protocol will tell us all the characteristics of that over-the-air fixture. And then we measure the device under test via our over-the-air fixture. And then it's just a standard embedding problem because we've figured out the characteristics of the over-the-air fixture before. And that actually works very accurately if all the requirements are met. Now I will move on. So basically what I've shown you so far is how we can formulate and calibrate this model. And there was this big digression on ambiguities. Now I want to get back to the main storyline, which was sort of reapping the benefits of strong coupling between tunable components. And the goal was to have a in-software model-based approach. So we formulated the compact model, we've calibrated it. Now what is left is optimization based on that model. And I will just sort of give a few brief hints of how that can be done in an efficient manner. The first concern that you might have when you look at that model is that when you have many tunable elements, this matrix that you need to invert becomes very, very big. And so if you need to do that many times, you might be concerned that that's too computationally expensive. Now, for optimization protocols that rely on many forward evaluations, examples being coordinate descent or dictionary search, actually we can very efficiently perform repeated forward evaluations for different configurations by updating the previous forward evaluation using a linear algebra property known as Woodbury identity. So that basically alleviates this concern of the big computational cost of inverting the matrix. And other inverse design approaches, of course, rely on some sort of gradient descent approach. And so here I want to mention that, of course, our model is differentiable. And so we can integrate it into any sort of hybrid analog digital pipeline. This is something we've looked at a couple of years ago, actually, in the context of optimizing a dynamic matter-difference antenna end-to-end for a given computational imaging problem. So basically, you can see the physical model in there, and we jointly optimize the parameters of the physical model that are tunable with the digital parameters so that the measurement is sort of aware of the task and select salient information as it does the measurement. And of course, we also know the gradients in closed form, which might be useful for certain implementations of optimization protocols. So with that, I'll wrap up. So what I hope I convinced you of is that in order to develop these extremely tunable wave systems, we want to maximize their sensitivity to the configuration, which is possible by maximizing the mutual coupling between the tunable elements. But that makes modeling and optimization more challenging. At least we cannot do it with the usual tools. But what I've shown you is that we can actually formulate, calibrate, and use efficient models for these strongly coupled systems. And as a byproduct, I showed you this virtual vector network analyzer idea. And with that, I'm happy to take questions.